Good morning, everybody. We are on the fourth day of our Gian short course, Elements on Smart Structures, and the first lecture today is on structure-borne sound. So what are the learning objectives for this lecture? You can describe what structure-borne sound is. You can distinguish between two types of waves in continua. Then you are able to explain how standing waves arrive and why standing waves are important for active vibration control, and why the solution approach for the equation of motion is based on this. Then you can explain what eigenmodes of a vibrating structures are and what orthogonality means in this context. You can also explain the idea of modal transformation. Can describe the effect of damping. We will only briefly visit this. And you can describe what the response behavior of a beam to an external excitation is and how eigenmodes act in this context. Why do we have a look at vibrations? I already mentioned for active vibration control, but also for structural health monitoring and for active noise cancellation. We need to have a look at the dynamic behavior. What is structure-borne sound? Structure-borne sound is the generation, transmission, and emission of time-varying motions in solid bodies at audible frequencies. And in practical applications, we want to avoid them or reduce and at least activate influence the structure-borne sound. And in this course, we have some assumptions, linearity. So we assume that geometry and material behavior is linear. We assume small deformations, linear elasticity laws, time invariance of the structural properties. So they will not change. No motion-induced energy input and viscous damping behavior. Structure-borne sound is a wave-like motion of a mass element in a solid. We have here a mass element which moves, and a distinction is made between the direction of motion and the direction of propagation. And this is also the basis to distinguish between two types of waves. In this case, for example, we have the direction of propagation in this direction, also the direction of motion, but we will have a look on that. These two types can be distinguished. Longitudinal waves, where the direction of travel of the wave is also the direction of motion of the element. And the second type is a transverse wave, where the direction of motion or the direction of oscillation is this direction, and the direction of travel of the wave is in this direction. So the directions are perpendicular to each other. And like we can define the wavelength in this sine wave, we can also define a wavelength in this longitudinal wave, which is at the compression points in the wave. I've brought a small experiment with me here in lecture, a steel rod, which we can excite and then see hear the first eigenmode of this. If we can find the vibration node here and then hold or bear the structure at its vibration mode, then we can excite it and also hear the vibration in the first eigenmode. So if you, here's the middle of this steel rod, and if you then excite it, you can feel, and I think you cannot hear it over there, but you can really feel and hear the vibration. And if you like, you can try it out. I've tried to mark the mid of the rod. Then you can do it on your own. You have really to hold it in the middle, and yes.
Just I'm trying what is the difference in sound if I hold
Ah, okay. Yeah, you can also try if you just hold it not in the middle, but 1 centimeter, then you can't excite it. It will not get in resonance, and you won't hit the eigenmode. Yeah. Yeah. I mean, you can also try to find these vibration nodes, but it's maybe harder to identify. Yeah. So this is an example for a longitudinal wave in a rod. We have the wave propagation and the movement of the particle and the wave propagation in the same direction. Yes, direction of oscillation and direction of propagation coincide. Characteristic quantities are particle velocity and stress. And in transversal waves, we have the direction of oscillation and the direction of propagation orthogonal to each other or perpendicular. And characteristic quantities for plane transversal waves are particle velocity and shear stress. For torsional waves, angular velocity and torsional stress. And for bending waves, we will have a look on bending waves later on, particle velocity, angular velocity, stress, sigma y, and also the shear stress. So if we have a closer look on the longitudinal waves, I quickly have to open the software to write on board. Then what we of course can state that a mass element like this is our mass element here, experience a strain in one direction. Epsilon x is the derivative with respect to space. And we have a stated linear material behavior. So sigma is equal to Young's modulus times the strain. So in other cases, not in smart structures, in this lecture, it would be the Young's modulus E. And now we can have a look at the differences of the force in this cross-section and this cross-section. And we have on the one hand stress times, or the force equilibrium. We have the cross-section A times the stress sigma x. No, this is the one side here. And at the second end or cross-section, we have this here. So we have in addition the change in stress times the cross-section. And this equals the inertial force of these element. So the difference between the stresses on the cross-section must be equal to the inertial forces. Then we can write it also like this. So the change of stress with respect to spatial, the spatial quantity equals the density times the, not the velocity, the acceleration of this structure. So using the vibration relation, we can, the vibration velocity, so the particle velocity u dot, we can obtain this equation from the last slide, and we can also have this equation from Hooke's law, derived by time. And if we use them, or if we then derive them with respect to space, so the first one with respect to space and the second one with respect to time, then we get this equation which shows a coupling of the the rate of change of stresses in space domain is coupled with the rate of change of stress in the time domain. And for this equation, for this wave equation, we have a general solution which has a left traveling and a right traveling part, which we will have a look at later on. And this is this fraction here is CL, which is the longitudinal wave propagation speed. Yeah, so the general solution contains a right and a left traveling wave. Why this is important, we will see a few slides later. As mentioned, we sorry, yeah. This one. So UX is cancelled out by transforming these two equations into this. Yeah. Here? This one. So it's from the slide before, we have the Young's modulus times the strain is the stress, and the Young's modulus can also be written as the strain can also written as the derivative of the displacement with respect to space. And now we replace the displacement by the particle velocity. So we replace u with u dot, and the Young's modulus does not change with respect to time. This is an assumption. So then we get u point derived, or the derivative of u point with respect to x, the partial derivative, and then we have sigma x also derived by the time due to this time derivative of the particle velocity. And so from Hooke's law, by replacing the displacement with the particle velocity, we get this. So back again at the bending waves, there are by far the most significant for our applications, for active vibration control, for structures like this, simply supported beam. And here the direction of propagation of the wave is again perpendicular to the direction of motion. So the direction of travel of the wave is in this direction, and the direction of particle motion is in this direction, and characteristic values are the velocity, the angular velocity, shear force, and bending moment. And like we did for this particle, we can have a look again at the force equilibrium, or at the moment equilibrium. We have a particle out of the beam again, where we have the shear force on this side, and also the moment on this side, and then we have the changed, or the slightly changed shear force with respect to space on this side, and I write it here, also the changed moment. And then we can have a look at the equilibrium again, like with the particle from the longitudinal wave. Again, we have the shear force at this place minus the shear force at this place has to equal out the inertial forces of the element. We have here the mass, so A times delta x is the volume times the density is the mass times the acceleration of the particle we look at. And then we can also have a second equilibrium on the moments, which is the moment on this side should equal the moment on this side plus the shear force on this side with the lever delta x, which is the length of the particle. And then we can take the limit. So we assume that delta x goes to 0. Then this here becomes the derivative of the shear force with respect to space. And we still have the inertial force. And maybe I take another color. This one is then the derivative of the moment. And here the delta x vanishes. So summarized, we have then this equation, second derivative of the moment equals the inertial force without the length of the particle. And then we use the Bernoulli assumptions again, like we did, that the displacement is minus z times the slope. Get to red again. And then the strain can be written like this as the second derivative. So not the slope, but the curvature. And this leads to the constitutive equation of the beam, that the moment, if we integrate the equation, then we get the bending stiffness times the curvature of the beam. So yeah, more or less the Euler-Bernoulli ODE. And with this, we get the equation of motion for the bending wave of the beam. Shear deformation and rotary inertia are neglected, like stated before. What we have in technical structures is, do you have a question? No, okay. Real engineering structures have a finite length, so waves cannot propagate to infinite, and depending on the boundary conditions, they are reflected. And we have a right and a left traveling wave, like we saw in the general solution of the particle of the longitudinal wave. So we have, for example, here a right traveling wave being reflected, and then we have a left traveling wave. And from this superposition of these two waves, we get so-called standing waves, which have nodes here and antinodes. So the shape of the wave does not change; only the amplitude changes by time. And we saw in the experiment in the beginning, where we hold the rod at the node, then we can excite the structure in the respective eigenmode. These standing waves correspond to the eigenmodes of a structure, which we will look at active vibration control later on. And the shape of these waves are defined by material geometry and also boundary conditions. And assuming these kind of standing waves, we can use the separation ansatz and have a solution for the wave equation, so the deflection of the beam, independence of space and time, with this function for the standing wave, just describing the form of the wave times the oscillation in time with this qt function. So this is the deflection of the eigenmode. The first derivative would be the rotation. The second would be corresponding to the bending moment, and the third would be corresponding to the shear force. This is important because the assumption of standing waves, and with this the solution approach with this separation ansatz are the basis for the following vibration control. So coming now to eigenvalues and modes. If we look at a simply supported beam, then we can describe the solution here from the external excitation of the free vibration with the sum of the description of this of the waveform times the oscillation in time, and the sum from 1 to infinity describes the overall behavior. So the sum of the eigenmodes of the structure. And for example, this is with a half wavelength, the first eigenmode of this simply supported beam. This would be the second eigenmode, and the third eigenmode is depicted in green. And each eigenmode vibrates in his eigenfrequency, which depends on, again, material parameters as well as cross-section of the beam and boundary conditions. And the corresponding eigenmodes can be described with a sine function with a factor for the amplitude and the bending wave number. So this is the idea to describe the vibration behavior of the simply supported beam. Of course, in real structures, it's far more complex than our simply supported beam. For example, these are natural mode shapes of an aircraft. I think it could be an Airbus A340 with 4 jet engines. And here, if you look from the top, here's the front, and here's the cockpit section. Here's the empennage. You can see the fuselage bending line, which means that here the cockpit section bends to the one side, and here is another eigenmode of the structure where it's curved in the other direction. From the solution for the wave equation here, the sum again of the description of each individual eigenmode with the oscillation in time with the respective eigenfrequency, we can have this kind of solution for each individual eigenmode. So this would be for eigenmode J, and this would be for eigenmode K. If we use this equation, put it into this equation, so derive it 2 times with respect to time and 4 times with respect to space, then we come to this equation here. And now we want to test something. We want to test if one eigenmode can perform work on the other eigenmode. And to do that, we multiply these equations with the other eigenmode. So we multiply this eigenmode k, or this description of the eigenmode k, with the equation or the solution for eigenmode j and the other way around. Then we perform some integration and subtraction actions. We come up with this long equation, carry out integration by parts twice at the right-hand side, because then we get a solution like this, where we can more easy or far more easy put in the boundary conditions of the beam. And then in the end, we come up with this equation. And what we can see from this, if this should be 0, the overall expression, and we say that we want to have that k and j are different eigenmodes, then they have different eigenfrequencies. So these are not equal. If they are not equal, then this can't be 0 here in front. And with this, it must hold that the integral is 0. And from this, we can state that we have orthogonality of the eigenmode. So the inertial forces of one eigenmode, a standing wave, does not perform any work on the other eigenmode with respect to mass distribution. And this is important because with this assumption, we can describe the vibration behavior in these eigenmodes, because they are clearly separated and do not interact with each other. And then we introduce another quantity. It's a generalized mass. We take this equation again, but now with the condition that j equals k, so both are the same eigenmode, have the same eigenfrequency. Then this integral at the end does not equal, or is not equal 0, because this one equals 0, and this is the definition of the generalized mass in for modal description. We will have a look at a few slides further where we will use it, why it's important. And eigenmodes are only defined up to a prefactor. We saw this prefactor for the amplitude, so we have only a description of the shape, but not on the absolute amplitude, and therefore the mass depends on the normalization of the eigenmode, and there are different approaches, the maximum norm or the Euclidean norm, to make them comparable between the different eigenmodes. So what is the generalized mass? This capital M for the eigenmode J in this case. It answers the question, how much of the structure's total mass effectively participates in mode J. So it is not a mass we can determine like a weight. It's dependent on the mode. So each eigenmode has its own generalized mass. And it's because of not all points of the beam move equally. So nodes contribute nothing to the motion, and antinodes contribute most, where the amplitude is highest of the standing wave. Yeah, and therefore, as said, each mode has its own effective mass. And it's not comparable with the physical mass of the beam. We can have a look at that. A simply supported beam here compared to a cantilever beam. Even if the beam itself is the same structure, so same cross-section, same material, but different boundary conditions, we will have a different eigenbehavior, so different eigenmodes, and therefore also the the generalized mass is different. So here it's 1/2 times rho times the cross section times the length, and here it's 1/4. So same beam, but different boundary conditions lead to different eigenmodes, lead to different generalized masses. Sorry. It's the come again. So I don't have prepared to derive these equations, to be honest, but I think it's this one. It's the bending wave number for the different eigenmodes. So it's for the eigenmode J then index changed. And with this we can perform a modal transformation. So with the separation ansatz, describing the eigenmodes and the time. This is also called the modal coordinate, because we assume standing waves. We can transform this structure simply supported beam, the first eigenmode, in a single degree of freedom oscillator. And the oscillator is defined by the generalized mass and the generalized stiffness, which is a similar quantity like the generalized mass transformed with the assumptions. So we have an equation like this: mass times acceleration plus stiffness times the modal coordinate q. And with this we can describe each eigenmode with this single degree of freedom oscillator, and when we sum them up, we can describe the overall vibration behavior of the structure by summing up all these single degree of freedom oscillators. Here are the definitions again, depending on dimension of the eigenmode. So how we normalize it, the generalized mass is given in kilograms or kilogram times square meter, and the generalized stiffness in Newton over meter or Newton meter. And this is what I already said on the slide before. So we can describe or treat each eigenvibration of a structure with the spring mass system. So the takeaway is, if we assume this general solution with the separation ansatz, so the spatial eigenmode with its standing waves, and the generalized modal coordinate, which describes the change in time, then the structure vibrates in this shape, and the time evolution of the vibration is described with this modal coordinate. And we can transform the beam with infinite dimensions or degrees of freedom, the real structure, in a set of independent single degree of freedom oscillators. And they are independent because we showed that one eigenmode cannot perform work on the other eigenmode. So we have a description for each eigenmode of the structure, where the modal mass and the modal stiffness depend on the problem on the beam with its boundary conditions. We could also include damping. We will not dive deep into it, just to give you an impression how this would work. We have the description of the standing waves with a factor for the amplitude. Then we can include in the modal coordinate a damping factor, and if we would excite this structure like this, then the oscillation would decay due to the damping of the structure. So now combining it with smart structures again, we could have a beam with an actuator applied on the whole surface. So this would be the structure of the beam. and here we have an actuator. Then we can describe the curvature of the beam, second derivative of W with this small signal behavior equation again, and we can integrate it 2 times and get and taking into account the boundary conditions, so we come up with a description of the deflection of the beam due to the actuator. KB, or I think it's kappa B, is I think it's curvature. No, I think it's not the curvature. I took some notes. Let me check. I think it's again the standing, the wave number. What I will tell you after the lecture. I will look it up in my documents. It should be the wave number again, but now as a kappa. And now we could apply an electric field on the actuator. So we deflect the beam with this expression, and then abruptly remove the electric field like you did yesterday in the lab. Then the beam would vibrate, and the vibration would decay again because the real structure is damped and it vibrates down from this deformation. Now we can have a look again at the force equilibrium we started with for the bending waves. Second derivative of the moment equals or equaled before the inertial forces, and now we have an external force acting on the beam due to a disturbance, for example, and it varies in space and in time. It's depicted here. So this is the force with respect to time and space, and it is an external vibration on the structure. Then we can have to include material damping also. So this damping term is also introduced, and then we can have a look at the excitation again and use a separation ansatz like for the general solution. So we split it up in a function describing the shape of the excitation and the change in time of the excitation, and then we can use again a modal transformation also for the excitation of the structure. We are using then with the modal transformation the orthogonality relations again, and now we have a description with a single degree of freedom oscillator again, but not only the mass and the spring, but we also have a damper now in it for the material damping, and we have this external excitation. Here it's stated as P, but it's the same as the F here. And the capital F is the generalized excitation compared to the generalized mass and the generalized stiffness. And this is in each eigenmode I. So we have a function for the, let's say, overall excitation with respect to space, and we multiply it with the eigenmode. So this is the share of the external excitation on this eigenmode I. And we can have a description for this again for each eigenmode, so that we have this system again for each eigenmode describing the vibration. So if we have if this is a large quantity, then our external excitation would have a strong, or would strongly excite our mode I, and if this here is small or 0, then the excitation is only weakly, or the structure is not excited at all. So we use it here to multiply the time-varying excitation. And if this is large, we excite this special mode largely, and if it's small or 0, then this mode we are looking at the moment is only weakly excited. If we go back to our simply supported beam again, then we can describe an external excitation with this time-varying distributed load. It's again, here's the P. I would correct it to F here. Then we can, for example, describe it with this sine function. So we have the amplitude, the sine, and sine from the wave number times the spatial coordinate x again for the generalized excitation. And if we integrate it, we come to this, and then we use the wave number again and put it in, and then we can have a look at the different f's for, or the different generalized excitations for different eigenmodes. And if we put in different values for I, which would be first eigenmode, second eigenmode, and so on, then we see that the even eigenmodes result in 0 here, because cosinus of 2p would be 1, and then we have 1 minus 1, we have here 0, and with that we have in total 0. So with this distributed excitation of the simply supported beam, we can only excite the odd eigenmodes of the structure. Now we can also have a look at, well, what we did before was looking at the time domain for the vibration response for each eigenmode. We can then use a Fourier transformation to also have a look in the frequency domain and describe the oscillator for each eigenmode with in the frequency domain. So again, we have here the generalized mass, the damping and the stiffness quantity and the excitation. And then we can transform this equation 45 to the equation 46. And here we have the external excitation with respect to frequency, so the spectral excitation. And then we have a transfer function including the generalized excitation for the eigenmode we are looking at. And with this, we can see how the modal coordinate of the eigenmode I in the frequency domain is affected by this external excitation. And then we have with this we can also formulate the description of the beam overall in terms of the space quantity and the frequency. And this is by summing up all the eigenmodes we have, so all the oscillators we are looking at. But as you might have seen on the slide before, the influence on the higher eigenmodes decay, so we don't have to look at an infinite number of eigenmodes, but just as at, let's say, the first eigenmodes which really have an impact on the vibration behavior on the overall beam. And we can state by this that eigenmodes act as filters with respect to the excitation spectrum. So the vibration response is based on a superposition of the excitation spectra filtered by the respective eigenmodes. And this can also be seen here. We have a general excitation, but the eigenbehavior of the structure filters the excitation so that only the odd eigenmodes are excited. Now, this slide is a bit crowded, but we will have a look. We assume that a beam again is excited with a broadband spectrum. So this is the excitation of the beam with respect to time. This is the same spectrum or the same excitation in the frequency domain. We use this in the frequency domain as an input to look at the different eigenmodes with our transfer function. And then we can see that only the modal coordinates are affected very differently. So the first eigenmode is excited here in the resonance. The second eigenmode is not excited at all, and the third eigenmode has only a small, or is only to a small share excited by this spectrum. And with this, we can then set up or describe the vibration behavior. So it would vibrate dominantly in this shape, it would not vibrate in this shape at all, and a bit in this shape. And I forgot, we look at especially this point, the vibration at this point at x equals L/4. And then we can calculate from this the excitation at this specific point here. And this is the filtered response of the structure to the general excitation here. So you can compare this. It's the unfiltered external excitation, and this is how the structure then vibrates, filtered through the different eigenmodes. And the response is characterized by the low frequency around the first eigenmode because this has the largest share or excitation in the vibration behavior. And with this, we can also describe the transfer behavior. So we could look at a point K here. This is excited by this broadband spectrum. And we want to know how this point L is affected by this external vibration. Then we can use an expression like this, where we again multiply the eigenmode or the eigenmode shape at the point K with the eigenmode shape at the point L times the excitation in the or the spectral excitation in the frequency domain, and then we can get a description of the deflection with respect to frequency at the point L. And this is this fraction here, or this sum of fractions here, is our transfer function from point K to point L. So, and with this, we are already coming to an end of this introduction to vibration and modal analysis. So, standing waves form the basis for our solution ansatz of the equation of motion, because then we can separate the description of the vibration or the shape of the vibration in the eigenmodes and the variation in time, the modal coordinate. We can describe the overall vibration behavior of the structure with the sum of their eigenmodes and eigenfrequencies, or with the sum of these single degree of freedom oscillators. And yeah, each eigenmode can be described by modal transformation with a single mass oscillator. And then the sum of single mass oscillator is describes the overall behavior of the structure. And eigenmodes act as a filter to the vibration response of structures to external excitations. So they don't vibrate in the same spectrum as the excitation is, but the vibration behavior is filtered by the eigenmodes of the structure. Do we have questions on this? Yeah. Yeah.
Transverse you can consider as a no force,
Mm-hmm.
but in this direction there is a net force.
Yeah.
So can you model this as a free vibration?
I'm not sure if I got the question right. So in aerospace structures, thin structures, we would also have these kind of bending waves and no longitudinal waves, I would say. Yeah. And we can use also this approach with the modal analysis also on the whole aircraft structure. Yeah. Yeah. The bending waves, or no, the standing waves occur in every structure. So every real structure has boundary conditions, is not infinite, and therefore we have these reflection of the waves. And normally waves are reflected several times before the material damping calms down the vibration. And therefore we can assume that standing waves are in each and every structure. And therefore we can describe real systems with this separation ansatz and the modal transformation. Yeah. And we in the next lecture on active vibration control, we will have a look at actuators placed on the structure and how they would interact with the vibration and how we can use them to calm down the vibration of a structure.
Thunderstorms also airplane.
Yeah.
We have net electric field.
Yeah.
So does it create any modes like does it create any contraction, expansion?
The electric field in an aircraft.
They're large electric fields.
Yeah, and
thunderstorms.
and the question is if they would create vibrations or would excite our actuators. I'm not aware of vibrations due to electric field. Maybe there are some, but not to an amount that or to an extent which matters. So we are looking only at excitations from the jet engines and aerodynamic loads of the structure and so on. And for example, yeah, it's more the also the landing and start phase, takeoff phase, for example, which could excite the structure. Yeah. I think it's not taken into account in the design of aircraft. So therefore, I would assume that it doesn't matter, but I'm not quite sure. Yeah. Okay, then I would say tea break before we start.